This video is about vectors. So what's a vector? A vector is an entity with both magnitude and direction. So this is a vector, and here's another one with a different magnitude and a different direction. The definition didn't say where those vectors needed to be in space, so we can place them on the Cartesian plane. So this one goes to here, and that one goes to there. To find their rectangular result, we can just add them. So they both have an x value and a y value, and they both have a name, blue and green. The x value of the blue one is 3, y value is 0, green, x value is 0, y value negative 2. The rectangular result is the addition of those two sets of numbers. So this is 0 and negative 2 is negative 2, and x is 3 plus 0, or 3. We can place that result in the correct position, 3, negative 2. Now there are two ways of representing a vector, rectangular and polar, and we get the polar result by joining the origin to the rectangular result. Now we need an angle between the positive x-axis and the vector itself, which we'll call r, and we'll call that angle theta. To find r, we take the square root of 3 squared plus negative 2 all squared, which gives us root 9 plus 4, which is root 13, which is 3.61. Now to find theta, we can say that theta is equal to inverse tan, which is tan to the negative 1 of negative 2 on 3. And this is equal to negative 33.7 degrees. So now we can say that r theta is equal to 3.61, comma, negative 33.7 degrees. Now, that's time consuming. So we can quicken things up by using our graphics. So let's do that. The rectangular to polar window is accessed via the options key. We write the vector 3, negative 2, then press EXE to give our result. 3.6 for r and negative 33.7 for theta. When using a calculator, it's a good idea to demonstrate good mathematical fluency. Let me suggest a method for translating calculator shorthand into good communication. To do this, we'll use two new vectors, blue one, 3 at 45 degrees, and a green one at 2, negative 30 degrees. So once again, we'll have an x value and a y value and a blue vector and a green one. So the x value of the blue vector will be 3 cos 45 degrees, which will be equal to 2.12. And for the y value, we'll have 3 sine 45 degrees, which will also be equal to 2.12. For the green one, we'll have the x value 2 cos 30, degrees, negative 30 degrees, and that's going to be equal to 1.73. And for the y value, we'll have 2 sine negative 30, which will be equal to negative 1. So we add those up and we'll get 3.85 for x and 1.12 for y. So that gives us our rectangular value, 3.85, 1.12. Now for polar, we'll add z equal to r theta, and r will be equal to the square root of 3.85 all squared plus 1.12 all squared, and that will be equal to 4. And for theta, it's always going to be tan to the negative 1 of the opposite on the adjacent, which is going to be 1.12 divided by 3.85, which will be equal to 16.2 degrees. So we can say that z is equal to 4, 16.2 degrees. We'll do this problem for a summary. First of all, we put all the vectors tail to tail on the origin. So this one goes to here, and that one goes to there. Notice that the blue one and the green one resolve easily. The yellow one has a value of 4, 3. So we add them up and we've got 0, 3, 4, 0, 0, negative 3, and negative 4, 0. So they add to 0, 0. This is true for any closed polygon of vectors. If this was displacement, for example, we could walk around that loop and our displacement would be 0. We'd be back at the origin. If this is true for displacement, it's also true for the vectors based on displacement: velocity, acceleration, force, and momentum. If we imagine, for example, that these vectors are force vectors, opposing pairs cancel, and the sum is again 0. I hope this helps, and all the very best.